In my last video, we introduced the concept of an absolute value graph and kind of explored what they look like. But we were able to kind of articulate that all absolute value graphs in general can be written in the form y equals some number a times the absolute value of x minus some number h plus k. In the last video, we were messing around with this a value to see what effect would that have on the graph of the most basic function, f of x equals absolute value of x, or y equals absolute value of x. And we were able to determine a few things, actually, that the a value would control vertical stretch, vertical shrink, but also whether it opened up or down. And also, we kind of figured out that a value is kind of like a slope. That is, when you look at the absolute value graph, absolute value graphs all look like these, look like this here. They have some vertex and some axis of symmetry that runs through the vertex there. And I suppose I should be sketching it in this way, but we say our axis of symmetry, and we have a vertex right here. But essentially, we were discovering what the a value had in terms of an effect upon the graph. What we're going to be doing in this video are really highlighting what values h and k do to our graphs here. So we're going to look at a few examples. We'll go through these pretty quickly. But it says, let's construct some tables for the following functions and then graph the solution points on the coordinate plane to see, well, what would our graphs look like? So in this first instance, we have some f of x, or y equals the absolute value of x plus 1. Okay. So I want you to notice here, we are exploring the effect of h upon our graph. And the reason why I say it's h is because when you look down here at this general form, h is always inside the absolute value bars with our x value, whereas k would be on the outside. And this a value is the number we're taking times our absolute value graph out front. So since we have these h values here, let's kind of explore what would happen to our graph. I'm going to say, excuse me, x and y, and let's throw in some x values here. I'm actually going to use -3, -2, -1, 0, and 1 on purpose. I kind of know what I want to highlight here. But if we were to plug these in, say for instance, 0 is always an easy one to plug in. What would f of 0 be? Well, we would get f of 0 would be the absolute value of 0 plus 1, which is the absolute value of 1, which is 1. So I would get 1 here when I plug in 0. If I plug in 1, well, then I'd say I'd get 1 plus 1 in here, and it would have been the absolute value of 2, which comes out to be 2. What if I plug in -1? So again, -1, if you put that in here for x and you add it to a positive 1, you'd get 0. And the absolute value of 0, of course, is 0. And then here comes the kicker. We say, well, what if I plugged in a -2? Now, -2, the absolute value of -2 plus 1. We would get the absolute value of -1, and here's the point where we say, well, we know this would be 1. It's positive. It's kicking out positives, okay? If we plugged in -3, we'd get the absolute value of -3 plus 1, and -3 plus 1 is -2, but the absolute value of -2 is 2. So what I want us to see here is if we were to graph all these, we say, well, -1, 0. Let me switch over to maybe a darker color here. -1, 0 would be here. And we say, okay, well, -1, 0, we have 0, 1 was on this graph. And then 1, 2. We say also -2, 1, according to my table over there, and -3, 2 is on my graph. So what I want you to see, what I want us to see, is essentially this. This looks a lot like our original functions that we were doing over here, like y equals absolute value of x, except for we weren't changing the stretch, or the vertical stretch or shrink. We actually shifted our graph. You notice that instead of starting at 0, 0, it actually shifted 1 to the left, and that has everything to do with this value right here. So we're going to look at now g of x. What if we were to make a table of values for this? And I just want to go a little bit quicker here. We say, well, the values I'm interested in plugging in, let's say, are 1, 2, 3, 4, and 5. And on, with intent. I have an idea why I want to do this. But if I plugged in 3, for example, 3 minus 3 is 0, and the absolute value of 0 is 0. And what if we plugged in 4? Well, 4 minus 3 is 1, and the absolute value of 1 is 1. And 5 minus 3 is 2. Absolute value of 2 is 2. Essentially, I want you to see that 2 minus 3 is -1. Absolute value of that is 1. So not -1, but 1. And this is going to give us a 2 here if you check all these. But when we go graph these this time, let me switch over to maybe like I don't know, we haven't used a purple. 1, 2 on our graph, that'd be this point right here. 2, 1, 3, 0, 4, 1, and then 5, 2. And we get this graph right here. So again, you notice that these two graphs have the exact same widths. They both open upward. It's just that this graph now has been shifted here 3 to the right, whereas the other graph right here was shifted 1 to the left. And like I said, it has everything to do with the h value. So what I want to do is I want to come up with a conjecture here. I notice that when our h value here looks like a positive 1, it shifted our graph 1 to the left. But when it looked like a negative 3, it actually shifts our graph 3 to the right. What do I think is going to happen when I graph the absolute value of x plus 5? My conjecture is that I think it's going to shift 5 to the left from 0, 0. And as a matter of fact, it actually does. Okay. So in all three of these instances, the one thing I want you to notice here is this. Our a value, this number out front, this number right here, was 1. Okay. So that's why we didn't affect the width as we did in the last video here, where we were changing the a values out front and seeing that it was causing vertical stretch or shrink. But we also found out in the last video that a is kind of slopey. So what I mean is this: if I think that this graph is going to shift 5 to the left, and I could make a table to kind of verify that this happens, why don't we just do that? We go 1, 2, 3, 4, 5. I'm going to draw a dot, and what I can say is I am very confident that this is going to be our vertex right here. And the vertex, by the way, I'm going to label it this time, is at negative 5, 0. Now looking at the a value, since we know that the a value is kind of slopey, slopish, a is there, we say from this point, since the a value is 1 or 1 over 1, I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, up 1, right 1, and this is going to keep happening. And the simple fact of the matter is this: we are already aware that there is an axis of symmetry running through this graph. So just by knowing the right side behavior of our graph, we could come up with the left side behavior of our graph and say, well, then I know that this point has to be on there, and so does this one, and this one, and this one, just because of the symmetric properties of all absolute value graphs. So what can be said about the effect of h upon the value of the function? Okay, well, what we can say is this: h is responsible for horizontal translation, responsible for horizontal, I'm going to write the English word here first, we say shift. Okay, and we can say also translation is kind of the word we use in math. Translation means to shift a graph. Okay. Also this, I noticed that when h said plus 1, it shifted 1 to the left, or minus 3, it shifted 3 to the right, or plus 5, it shifted 5 to the left. But we can say this: we say h seems backwards. Okay, so this is kind of an important thing to note here. H seems backwards. Okay, so now why don't we go mess around with this k value? And I want you to notice this: when we look at this general form down here, we say, well, a is the number I'm multiplying by absolute value. H is this number on the inside here that we just found out is dishonest and shifts left and right. What do I think k is going to do to our graph? So really quickly here, let's go ahead and throw together a table. And the nice thing about this table is I'm just going to run with negative 2, negative 1, 0, 1, and 2. And plugging these in, I'd say, well, absolute value of 0 is 0, but plus 1, now I'm up at 1. We say, well, what if I plugged in a 1? Well, absolute value of 1 is 1, but plus 1 is 2, and then this one's going to give me a 3. And again, what if I plugged in negative 1? Negative 1, the absolute value of negative 1 is still a positive 1. So 1 plus 1, I get 2, and then here I'm going to get 3 also. So to sketch this graph, we'd say, well, not the point 0, 0, but the point 0, 1 is on my graph, okay? And the point 1, comma 2 is also on this graph, and 2, comma 3. And so again, there's this symmetric property going on, but what I want us to see is already, probably you've got this figured out, but that our graph from the original graph of y equals the absolute value of x, where we didn't do anything to it, this has just been shifted up 1. So I notice that this positive 1 right here has an effect of taking all of our original y values and just adding 1 to them. It's going to shift our graph up 1. So likewise, what if we were to look at g of x? What conjecture could we make here? Well, it's got a negative 3 for a k value. Do we think it would shift down 3? So I'll switch over to purple here, negative 1, negative 2, negative 1, 0, 1, and 2. If you plug all these in, like 0, the absolute value of 0 is 0. But if you take away 3, you're going to get negative 3. Okay? And if you were to plug in 1, you get 1. All right, well, 1 minus 3 is negative 2. And then again, we say, all right, well, plug in a 2, absolute value of 2 is 2 minus 3 is a negative 1. So these, because of symmetry, these kind of repeat also, but we say, well, negative 2, comma, negative 1 would be this point right here. Negative 1, comma, negative 2 would be this point right here. 0, comma, negative 3, obviously our y-intercept would be there. And then it kind of creeps back up again here. So what we can basically draw a conclusion from here is this. We didn't change the width of our graph because, again, look at the a value on all of these is 1, so I didn't do anything there. We didn't include an h value in here with any of our x's this time, so it didn't shift left or right. But we can basically say this k value is responsible for what we call vertical translation or vertical shift. So we say, k is vertical shift or translation. And we notice that unlike the h value, k seems honest. And by honest, I just mean that when it says -3, it actually indeed shifted down 3. So here's the very, very last thing that we want to kind of synthesize from this entire experience in this video, but is this. When you look at anything of this form, y equals a times a quantity x minus h in absolute value bars plus k, what we can say is, well, if we had no h or k value, that is, if it looked like this, and this was kind of like in our last video, then it didn't shift at all. I mean, I can show you this. None of these graphs right here shifted. The a value was just changing its width and how it opened up or down. But when you talk about h and k, we say usually when there's no h and k, it starts at the origin. But what if I were to say I shifted left or right h units and I shifted up or down k units? Then I would be at some new point that we could call HK, because I would have been leaving from 0, 0 and going h units left or right, k units up or down. Now I'm at the point HK. So this is always true, but the vertex of any absolute value graph is at the point HK. I almost wrote X. We say HK, where this is a liar. The H value is a liar and K is honest. Okay, and furthermore, we say the axis of symmetry. We want to make sure we write this down. Axis of symmetry. We can write AOS. That is, appropriate, an abbreviation there. But we say it's this vertical line that goes through our vertex, but it has to have the same x value as our vertex because it goes through the vertex. But this is true of every absolute value graph. So putting together what we know in the next video, we'll say, well, I know what A does to my graph. I know what H does to my graph. I know what K does to my graph. Let's start sketching these without having to make a table every time.